An understanding of rotation matrices is helpful for identifying situations in which oscillations can be supported by dynamical systems in physics, engineering, and biology. This slide deck is divided into two videos. In this first video, we construct rotation matrices, and then in the next video, we explain that complex eigenvalues are a hallmark of rotational dynamics in dynamical systems. To introduce the concept of a rotation matrix, we illustrate the concept of rotating a vector. In the xy plane, draw a blue vector v. Obtain another vector v' by rotating without scaling. Our goal is to write a matrix whose elements relate the new yellow vector v' to the original blue vector v. Yellow vector v' has the length of blue vector v, written as v in italic font. The original blue vector v makes an angle phi with the x-axis. The new yellow vector v' makes an angle theta with the old vector v. Using the x and y axes to define a coordinate grid, we observe that the components vx and vy of the original blue vector are v cosine phi and v sine phi, respectively. Likewise, the components of yellow vector v' are v cosine of phi plus theta and v sine of phi plus theta. Using angle addition formulas, including the one we demonstrated in the video on trigonometric identities, we can re-express the trigonometric functions of phi plus theta in terms of products of trigonometric functions of phi alone and trigonometric functions of theta alone. Multiply the number v distributively. Recognize v cosine phi as vx and recognize v sine phi as vy. Switch the order of the terms in the bottom component so that the term with vx appears first. Perform finger exercises to confirm that the components of the blue vector v can be arranged off to the right as a column vector as shown. Together, the matrix of trigonometric functions and the blue column vector provide the components of the yellow vector v'. This matrix equation represents the rotation of the blue vector v by a so-called rotation operator r hat, which yields the rotated yellow vector v'. The rotation operator is parametrized by theta, indicating the particular amount of rotation it provides. The matrix representing the rotation operator is called a rotation matrix. The rotation matrix that we have introduced can be used to describe the repeated incremental rotation of a vector in space. On the xy plane, draw the blue vector v represented by components vx and vy. Applying the rotation operator r hat once is represented by multiplying once by the rotation matrix. Hitting a second time with the rotation operator r hat corresponds to multiplication a second time by the rotation matrix. A third rotation corresponds to a third matrix multiplication, and so on. If we have a dynamical system in which a rotation matrix is used to express the system state at one step in time in terms of the system state at a previous time step, then we know that the dynamics of the system will correspond to walking around a circle in angular steps of theta. It becomes easy to sketch and describe the long-term dynamics of the system. What if we were presented with decimal numbers? What if we were working abstractly in terms of unknown parameters? How would we analyze decimal representations or variable names to determine whether a dynamical system of interest exhibited motion around a circle? In this video, we introduced the concept of a rotation matrix, which represents the action of a rotation operator on a vector. In the next video, we show that rotation matrices have complex eigenvalues. This will help us to understand that complex eigenvalues are a hallmark of rotational dynamics in dynamical systems.